Welcome back. We're going to look at Lesson 5, Evaluating Logarithms today, and we actually have already looked at that with Lesson 4 a bit. With this example here, evaluating basically means finding the value of the logarithm, but we've been doing that already because you know that the value of the logarithm is really just the exponent if you can make what's inside the log a power with the same base as the log. So this here is another way to do it. Myself, I personally like just going log base 2 and writing 8 as 2 cubed. And then, of course, that would just equal 3. But what this demonstrates is if you let it equal some variable and then get rid of the log, so that would then be 8 equals 2 to the v, and then get the bases the same, exponential equation, right? Get the bases the same on both sides, and therefore the exponents would equal each other, and v would equal 3, and then back to here, so it equals 3. So you can see where you wouldn't really use that method if you could do it the simpler way. Sometimes if you have, say, something like log base, let's say base 125, and then you have a 5 in here, that's a little bit trickier. Like you might recognize that 5 could be written as 125 to the 1/3, but if you don't, then that method might work quite well. So we raise the base on both, or raise the to the exponent on both sides. We'd have 5 equals 125 to the x. Replace 125 with 5 cubed, and then the x is still on the outside. Okay, so 5 to the 1 equals 5 to the 3x, and therefore the exponents equal each other, and you discover that x would equal 1/3. So in other words, the value of that log base 125 of 5 is 1/3. So that might be a situation where it's not obvious by changing 5 into a power base 125 what the value of that would be. But most of the time on these ones here, I would just simply, let's try the first one, focus on finding 81 as 3 to some exponent. So 81 could be written as 3 to the 4, and therefore the log is the exponent. The log of 81 would be the exponent because the bases are now the same, so that equals 4. Okay, so let's try the next one. Actually, why don't you guys try the remaining 3, B, C, and D. Pause your video and we will check our answers when you're finished. So pause now. Okay, so did everyone get answers of 3 and then 1, because log base 707 to the 1, that would equal just the exponent 1. And then finally on D, did you guys get 0? That one's a little bit trickier to see, but 1 can be written as a power with base of anything, really, as long as the exponent's 0. But in this case, we need base 12, so 12 to the 0 is equal to 1, and therefore the log of base 12 of 12 to the 0 would be the exponent, which is 0. So you're starting to get now that you know what the value of the log is. Let's take a look at the next page. Okay, so kind of more of the same here. If our base was b, we can still do this. The value of log base b of 1, if we can write 1 as b to some exponent, and of course that could be b to the 0, then that would be the exponent, which equals 0. All right, and the next one, very similar. What's the exponent on b? It's a 1. Bases are the same, so therefore that just equals 1. All right, example number 3. 2 log base 8 of 512. Well, that 2 can stay out front, and we can focus on writing 512 as 8 to some exponent. You can try it on your calculator if you like, until you get that. And let's see, that would be to the 3, I believe. 8 cubed gives you 512, and therefore log base 8 of 8 cubed would just be the exponent, which is 3, and now we have 2 times 3, which is 6. Good. Why don't you guys try B and C and see if we get the same answer, and then we'll move on to example 4. So pause your video now. Okay, so on part B, we wanted to write 32, first of all, as 2 to the 5th. But that's not good enough to have 1 over 2 to the 5th, so then we would bring that power to the numerator, creating 2 to the negative 5th. Negative 5, sorry. I'm not sure why I was saying 5th. Anyways, 2 to the negative 5, and therefore now the log value would just be the exponent, which is negative 5. Okay, on C, we have 120, the square root of 125 inside log base 5. So 125 you probably recognized as 5 cubed. And then a square root is really just a fractional exponent. So the 3 goes on top, the 2, indicating the square root, goes on the bottom, and so the root of 125 becomes 5 to the exponent 3 over 2. And now that would just equal the exponent because the bases are the same, so the answer is 3 over 2. Good. Example number 4, super easy already because we have dealt with that in a different way. Logs and exponents are inverse functions of each other, so if you have 5 to the exponent log base 5, that is just going to equal, you got it, 25. So you could probably guess what the next two are. I'll give you a second to write those down. Okay, so that goes 49. That goes 27. Super easy, right? The only way that might get a little more complicated would be if you had something like 9 log base 3 of, say, x or something. Okay, so then you know the 9 and the 3 are connected, but you'd have to replace 9 with 3 squared. Okay, and then this involves a rule that we're going to learn in lessons 6 and 7, where this 2 can go back into the exponent because obviously we can't cancel off the 3 log 3 because the 2 is in the way. So we would move that back into the exponent. That's a power rule that we'll learn in lesson 6, and then that could go and you'd get x squared. Okay, but if it's just like this, very simple, they're inverses of each other, so that's what it would turn into. So if you had log base a to the log base a of n, what's that going to be? That'll just be n, of course. Okay, let's look at the next page. Okay, we're going to look at evaluating logarithms using change of base, but before we do that, we're going to look at estimating what a log would approximately be. That's a curriculum objective that we need to do. So essentially what we're going to do is we're going to figure out, using some benchmarks, approximately what log 50, base 5, would be between. So what's a power of base 5 that we know that's, say, less than 50? I'm thinking 25, right? Because 25 is 5 squared. And another one, let's see, 5 cubed is 125, right? So I could basically say 50 is somewhere between 25 and 125. And those are both powers of base 5. So let's put the values of these. Log base 5 of 25. 25 is 5 squared, so therefore that would be just 2. Okay, and log base 5 of 125. 125 is 5 cubed, so therefore the exponent, 3. So log base 5 of 50 should be somewhere between 2 and 3. Now, choosing one of these choices they've given below, definitely not between 1.5 and 2 because it has to be between 2 and 3. But the question is it closer to 2 or closer to 3? Well, I'm thinking because 50 is a little closer to 25 rather than 125, I would probably choose that it's between 2 and 2.5. Okay, we're going to learn how to do that on the calculator in, well, in a few minutes, if not less. Okay, now, something called common logarithms. There's a logarithm that is used a lot in science, and that's a logarithm with a base of 10. So as a result, rather than continuing to write base 10 all the time, it was basically understood in the science and math world that we were just going to write log without a base, and that would be assumed to be base 10. Okay, so if you hear someone mention common logarithm, that means base 10. Or if you don't see a base on your log, you assume it to be base 10. And the cool thing about common logarithms, or log base 10, is there's actually a key for that on your calculator, and that's the log key, and that means log base 10 on your calculator. Okay, so what we can do is find the value of this. Now we can do that not by converting to exponent form, but by writing 10,000 as 10 to some exponent. Well, it's sort of exponent form. So that'd be 10 cubed. So the value of that would be 3. Okay, try it on your calculator. Go log of 1,000 on your calculator. And what are you getting? Yep, you got a 3. Good job. Okay, example number 6. We're going to do a little estimating first, and then we'll figure it out, the value out on the calculator. So log base 10 of 89 we've got, and log 2000. They are both base 10. They wrote it here, they didn't write it here, but it's still assumed to be base 10 if you don't write it. Okay, let's see if we can find some benchmarks. What would be some benchmarks that would be between, that 89 would be between? So let's think powers base 10. So 10 to the 1 is 10. 10 to the 2 is 100. Yeah, that would be between. So let's use 10 as a benchmark, and also log base 10 of 100, which is also log base 10 of 10 squared. Okay, so those two would equal 1 and 2. So this number has to be between 1 and 2, but let's see if we can get it a little more specific. Is 89 closer to 10 or closer to 100? Well, probably closer to 100, so we could probably put it between then 1.5 and 2 rather than between 1 and 1.5. And there we go. Do it on your calculator, go log 89, and what do you get? Okay, so we should have gotten 1.95 rounded to the nearest hundredth. Okay, let's do the same thing with log 2000. First, estimate using a couple benchmarks of powers of base 10, and then we'll do it on the calculator. So you guys go ahead and do that, and then we'll check back in a minute. Okay, pause your video, please. Okay, so we used benchmarks of 1000 because that's 10 cubed, and therefore the log of 10 cubed would be 3, and 10,000, which is 10 to the exponent 4, and log base 10 of 10 to the exponent 4 would just be the exponent 4. So we're landing somewhere between 3 and 4 for an estimate, and 2000 is a little closer to 1000, so I'd probably choose then the log of 2000 to be between 3 and 3.5. Okay, you do it on the calculator, and we get a log 2000 to equal 3.30. So awesome, that worked out really well. Let's look at the next page. Okay, natural logarithms are going to be important later on if you decide to take calculus, but because they occur often in real life situations, finance and science, but they are not in the 30-1 curriculum, so we are not going to cover this in great detail, but basically natural logarithms are logarithms that are base e, and e is simply an irrational number. It's approximately equal to 2.718. It's kind of like pi, it keeps going forever, non-repeating, non-terminating. And so ln on your calculator means natural logarithm, and it basically means log base e, okay? So those two things are exactly the same. All right, so we'll move on and we'll take a look at the next page. And if you are interested, you can please see your teacher to go through what this is. But you will cover that in calculus if you decide to take that course. Okay, so this is our change of base identity. It's not on your formula sheet anymore. And the reason why is because they wanted to stress the importance of actually evaluating these logarithms, the ones that you can, evaluating those by hand. So this is no longer given, but this would be one way to evaluate the logarithms if you needed to do that. So in other words, what this change of base identity is if you don't have log base 10, so like for instance on this question here, C, we have log base 7, but 512 is not going to be expressed as 7 to some exponent. It isn't a power of 7. So you could, on your calculator, go log of the bigger number, 512, and notice I'm not putting a base, which means base 10, over log of the base, which is 7. Okay, and that, if you put that in the calculator, would give you the value of that. Okay, so why don't you guys try A and just see if you can get a value for that, see if we get the same thing. Okay, pause your video, please. Okay, so on the calculator, you used your change of base identity, and you went log 221 for this, log divided by log 5, the base, and we should have got a value of 3.35, keeps going forever, but to the nearest hundredth, 3.35. Okay, so like I said, not really part of the curriculum, so for interest's sake though, let's look at the next page. Okay, example 9 we won't need to do, not in the curriculum. And these ones we have kind of talked about already, but if you guys would like to do each of those, I'll put the answers up. So if you want to pause your video, and then we'll check the answers in a minute. And you guys can do all 4 of those without your calculator. Do them by hand, okay? Pause your video. Okay, running out of time, but if you check your answers, you might want to pause the video before the time runs out in order for you to check your answers in your work. All right, we'll see you next time. Thanks for listening.